Less than 1% of the people on this planet right now know that a previously unmapped volcano is actively erupting underneath the Pacific Ocean, north of Papua New Guinea, in a part of the central Bismarck Sea where nobody had been looking for a volcano. The eruption began on May 8th. It has not stopped. It has reorganized. It has pulsed. It has gone quiet on the surface while the ocean's underwater listening networks were picking up the loudest signals of the entire eruption. It has now sent pumice rafts onto the shores of inhabited islands while pushing an ash plume more than 5 kilometers into the sky. The volcano now has a name. The depth of its active vent does not. The cone it may be building has not been mapped. And in this exact arc of the Pacific, just 200 kilometers south of where this volcano is erupting, the last submarine collapse killed several hundred people through a tsunami the warning systems were not designed to forecast. The depth that controls the tsunami risk tonight is the depth that scientists openly admit they cannot confirm. One thing before we get into it: if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss the next debrief. Also, leave a comment with where you're tuning in from tonight. Let's dive in. Part 1. The ocean just started talking again. On the night of May 28th, in the Pacific Ocean north of Papua New Guinea, a network of underwater sensors picked up a sound that the same sensors had not been hearing for almost a week. It was not a single sound. It was a pattern. Low-frequency pulses, rising and falling in a rhythm that does not occur in nature unless something underneath the water is releasing gas, fracturing rock, or pushing fragments out of the seafloor under enormous pressure. The pattern grew sharper into May 29th, and then the ocean kept making it. What those sensors were listening to was a volcano that we still cannot directly see. It is somewhere between 500 and 600 meters below the surface of the central Bismarck Sea, although nobody can tell you that depth with full confidence, and the people who study these systems for a living are openly saying that. The volcano has only had a name for a few weeks. Its name is Titan Ridge. It is roughly 82 kilometers south of Rambutio Island, roughly 125 kilometers southeast of Manus Island, in the Admiralty Islands province of Papua New Guinea, and it is currently in the middle of an eruption that began on the morning of May 8th. That eruption appeared to be quieting down. Then it stopped quieting down. Then the ocean started talking again. If you have been here for a while, you already know part of this story. We covered the initial detection of this submarine volcano at the start of its eruption, when scientists had not yet given it a formal name, and the system was being called, very awkwardly, the Central Bismarck Sea Volcano. Since then, 3 specific things have changed. The volcano now has a name. The 2 vents that were producing the initial plumes have reorganized into one, and after a period of apparent calm, the system has produced a new and more energetic pulse of activity that has reached the people who live within range of it. So what you're about to hear is not a recap of the eruption. It is an update on what the eruption has done while we were watching for it to fade. The most important fact about this volcano, the one that controls every part of what comes next, is that we do not know its depth. That is the single most important sentence I'm going to say in this video, and I'm going to say it more than once because the depth of the active vent is the parameter that decides everything. Depth controls how violently the eruption can release energy. Depth controls how tall a plume it can push through the water column. Depth controls whether seawater and magma interact gently or explosively. Depth controls whether a growing cone on the seafloor can become unstable and slide. And depth controls whether a sudden movement of the volcano's flank can displace water badly enough to send a wave toward an island. Every one of those questions has a different answer, depending on whether the active vent is 1,500 meters down, or 1,500 feet down, or somewhere in between. And we do not know which of those it is. The people running the instruments do not know either. NASA's Earth Observatory has stated openly that the exact depth of the active vent at Titan Ridge is uncertain. The Smithsonian Global Volcanism Program, which maintains the official international catalogue of volcanic eruptions, has the same caveat in its entry for this system. The reason is not that the data is being hidden. The reason is that nobody has conducted a recent high-resolution bathymetric survey of the actively erupting structure. Bathymetry, the mapping of seafloor depth, is the most basic thing we know about a submarine system, and at Titan Ridge, the most basic thing is exactly the thing we do not have at the resolution we need. The volcano is erupting in a part of the ocean that has been poorly mapped. It is erupting through a structure whose precise geometry was not characterized before the eruption started. And right now, scientists are reading the surface of the ocean, listening through hydroacoustic networks, watching satellites pass overhead, and trying to infer what is happening in a chamber several hundred meters below the seafloor that they cannot directly see. That last part is the part that makes this volcano different from almost any other volcano you have seen us cover. When Mayon erupts in the Philippines, you can put a camera on the rim. When Kilauea is in eruption in Hawaii, you can fly a drone over the lava lake. When Etna throws a paroxysm, the satellite imagery shows the cone, the crater, the lava flows. With Titan Ridge, you can do none of those things. You can see steam reaching the air, you can see discoloured water, you can see floating pumice rafts, you can detect a thermal anomaly from orbit, you can listen with hydrophones, but you cannot put a camera at the vent. The vent is hidden by hundreds of meters of dark, cold, high-pressure seawater in a location where no instrument has been placed in advance because nobody knew this volcano was going to erupt. So when the hydroacoustic signals surged on May 28th and May 29th, what those signals were telling us was that the part of the eruption we cannot see was getting more active, while the part of the eruption we could see, the surface plumes, had been getting quieter. That mismatch is important. It is the kind of pattern that tells you the ocean is filtering what you can detect, and the ocean has been hiding a meaningful amount of the eruption from the satellites the whole time. And then, between June 1st and June 4th, the volcano stopped filtering. The Mirova satellite-based thermal monitoring system, operated jointly by the universities of Turin and Florence, picked up a strong thermal anomaly at the site on June 2nd. By the morning of June 3rd at 10:40 UTC, Mirova recorded a thermal power output of approximately 201 megawatts, using the combined detections from the MODIS instruments on NASA's Aqua and Terra satellites and the Sentinel satellite series. 201 megawatts. To put that in perspective, the baseline thermal signal from Titan Ridge in the prior weeks had been moderate, peaking at around 96 megawatts on the heavier days. The June 3rd pulse was more than double the prior baseline. By the standards Mirova uses to classify volcanic thermal output, 100 megawatts is the boundary into the high classification. Titan Ridge crossed that boundary cleanly, and it did it while the ash plume above it was reaching 12,000 feet, with VC Darwin issuing advisories to aviation, and within 24 hours, that plume was reaching roughly 5 kilometers above sea level. 5 kilometers. From a volcano that is supposedly buried under 500 or 600 meters of seawater that we cannot precisely measure. 5 kilometers of plume, 201 megawatts of thermal output, a hydroacoustic surge that started while the surface looked calm, a vent reorganization that nobody predicted, and a seafloor structure whose depth we cannot confirm. That is the situation right now. And the most dangerous mistake you can make watching this eruption is to look at the thermal chart, see the last reading drop back down to single digits, and conclude that the danger has passed. A submarine volcano can pulse, it can rest, it can pulse again. The chart does not show you a dead volcano. The chart shows you a volcano that is breathing. So tonight, we're going to walk through this eruption end to end. We're going to start at May 8th, when this volcano first announced itself. We are going to walk through the two-vent geometry that emerged in mid-May. We are going to look at the May 22nd earthquake that officially did not matter, but may have mattered. We are going to listen to what the ocean started saying on the 28th. We are going to watch two vents become one. We are going to climb that thermal pulse from the seafloor to the sky. We are going to land on the depth question and stay with it until you understand why it is the question that controls everything else. We are going to follow the pumice rafts onto the shores of the Admiralty Islands and meet the fishermen who are dealing with them. We are going to compare what is happening here to what happened at Ritter Island in 1888, 200 kilometers south of Titan Ridge, when a flank collapse generated tsunami run-ups of 15 to 50 meters and killed several hundred people. We are going to talk honestly about Hunga Tonga, the 2022 eruption that the warning systems were not designed to forecast, and what Tonga changed about how the Pacific track systems like this one. And we are going to end with the deeper mystery, the one that is not really about Titan Ridge at all, the one that is about how much of the volcanism on this planet is happening right now, somewhere below us, in a part of the ocean we cannot see. But to get there, we have to start where the volcano started. We have to go back to the 8th of May, to a small swarm of earthquakes, and to the moment when NASA's satellites caught the first plume rising out of an ocean that had been silent over this location for 54 years. Part 2. What surfaced on May 8th. On the morning of May 8, 2026, at approximately 1 in the morning UTC, the seismometers that ring the central Bismarck Sea recorded a small swarm of earthquakes. The events were not large. Individually, none of them were the sort of earthquake that makes a headline. Together, they had the spatial and temporal signature that geophysicists recognize as a magma intrusion. Multiple events clustered in time, clustered in space, distributed across a band roughly 12 to 30 kilometers from a single notional center, occurring over a few hours and then settling down. It is the signature of fluid moving through rock under high pressure. It is the signature, in this case, of magma cracking its way upward toward the seafloor. Within hours of that swarm, NASA's Aqua and Terra satellites passed over the area on their normal sun-synchronous orbits. Both satellites carry the MODIS instrument, which captures visible light imagery of the Earth's surface. Both satellites captured something that nobody had been expecting to see at that location: a steam-rich plume rising from a point in open ocean in a part of the Bismarck Sea where no active volcano was on anyone's list. That was the first surface evidence of what we now call Titan Ridge. The location is worth fixing in your head. The plume was rising from approximately 3 degrees south latitude, approximately 147.8 degrees east longitude. In practical terms, that puts the eruption roughly 82 kilometers south of Rambutio Island, and roughly 125 kilometers southeast of Manus Island. Manus Island is the largest island in the Admiralty Islands group, which sit at the northern edge of Papua New Guinea. The Admiralty Islands have a long history with the Bismarck Sea. They sit on the boundary between the South Bismarck microplate and the North Bismarck microplate, two small tectonic plates that are converging against each other at a rate of approximately 80 to 100 millimeters per year along the New Britain Trench. For context, that is a very fast convergence rate by global subduction zone standards. The Bismarck Arc is one of the most tectonically active regions on Earth. It produces earthquakes, it produces volcanoes, it produces the conditions under which a previously unknown submarine volcano can announce itself with a small swarm and a steam plume on a Friday morning. The plume was the easy part of the detection. The harder part was figuring out what was producing it. There was no volcano on the international catalogues at that exact location. The Smithsonian Global Volcanism Program, which maintains the master catalogue of volcanic systems worldwide, did not have an entry for this specific point in the Bismarck Sea. There was, however, a record of a single prior submarine eruption in this general region. In 1972, a submarine eruption was catalogued approximately 16 kilometers northwest of the May 8, 2026 plume location. That 1972 event was itself unusual. It was detected primarily through acoustic signatures and through reports from passing ships, because the seafloor in this area had not been mapped at high resolution then either. The volcano that produced the 1972 eruption was not given a formal name. It went into the catalogue as an event without a permanent classification, with a question mark next to its precise location. That is 54 years ago. Between 1972 and 2026, the system did not erupt again, as far as anyone can tell. There were no catalogued events at the site. There were no large earthquakes that would have indicated stress release on a major scale. There were occasional plumes reported in passing by ships and by the Darwin Volcanic Ash Advisory Centre over the broader Bismarck Sea, but nothing that pointed specifically to this location. For 54 years, this volcano either did not exist as an active system, or it was quietly waiting underneath several hundred meters of seawater for the right pressure conditions to push magma back to the surface. The May 8th swarm and plume tell us it was the second one. It was waiting. The first satellite passes after the May 8th swarm caught more than just a steam plume. They caught discoloured water surrounding the plume source. The ocean colour sensor on NASA's PACE satellite, which is sensitive to differences in the optical properties of seawater, captured the disturbed water around the eruption site in shades of brown and pale yellow against the deep blue of the surrounding ocean. Discoloured water is one of the classic indicators of a submarine volcanic eruption. It can mean several things at once. It can mean that sediment is being lifted off the seafloor by an ascending gas plume. It can mean that volcanic fragments are being suspended in the water column. It can mean that mineral-rich water from a hydrothermal system is being injected into the upper ocean. In the case of Titan Ridge, the early discoloration extended approximately 8 kilometers from the apparent vent location. That is a substantial footprint, and it tells you that the eruption was not subtle. The satellites also caught the first signs of floating pumice. Pumice is what happens when magma rises rapidly toward the surface and releases its dissolved gases all at once. The gases expand. The magma cools as it expands. And what you end up with is a glass-like volcanic rock filled with so many small bubbles that the bulk density of the rock can be less than the density of water. Pumice floats. It is the only kind of rock that does this routinely. In the days after May 8th, satellite imagery began catching bands of light-coloured material drifting on the ocean surface near the eruption site. Those bands grew larger over the following weeks. By May 25th, pumice rafts covering more than 69 square kilometres were visible to the west of the eruption. Bands of pumice extended up to 200 kilometres from the source. The volcano was producing real volume, and it was producing it consistently enough for the rafts to persist on the surface against the wind and the currents. Now here is the thing about submarine volcanic eruptions that gets lost when you describe them through the surface signals. The surface signals are downstream. They are the signature of something happening on the seafloor. They are not the eruption itself. The actual eruption is happening at depth, in a chamber and a vent system that nobody had mapped in advance, in a part of the ocean where the standard tools of volcanology do not reach. The Rabaul Volcano Observatory, which is the official monitoring authority for volcanoes in Papua New Guinea, runs an excellent network of seismic and acoustic instruments. But those instruments are positioned to detect signals coming from systems we already know about, in places we have already mapped. Titan Ridge was not on that list until May 8, 2026. From May 8th onward, the observatory has been doing what every monitoring authority does when a new system appears. It has been using the instruments it has, the data it can get from international partners, and the satellite imagery from NASA, the European Space Agency and other sources, to build a picture of what is happening from indirect evidence. That picture is detailed. It is also incomplete, and the gap between what we can see and what is actually happening underneath is exactly the gap that makes this volcano harder to assess than the ones we're used to seeing on the news. In the days after the May 8th detection, the Rabaul Volcano Observatory issued its first advisories. Geomar in Germany, an independent ocean research institute, confirmed the eruption from its own satellite analyses. The Smithsonian Global Volcanism Program assigned a catalogue entry. The volcano started getting attention, and the question that nobody could fully answer began to take shape. What exactly is this thing? What does it look like underneath the water, and what is it going to do next? Part of the answer came from looking at the structure that the eruption was happening on. The Bismarck Sea floor in this area is part of a feature now called the Titan Ridge. A ridge, in oceanographic terms, is a long elevated structure on the seafloor, typically aligned along a tectonic boundary or a chain of volcanic centres. Ridges can host multiple volcanic vents along their length. They are not single-point sources. They are structural features that can produce eruptions at different locations at different times, depending on where the magma supply finds its easiest pathway. The Titan Ridge feature has not been mapped in detail. Some of what we know about it comes from older, lower-resolution surveys. Some of what we know comes from inference based on the spatial pattern of the May 8th earthquake swarm, which suggested an elongated active region rather than a single point. That distinction matters. If Titan Ridge is producing eruptions from a ridge structure rather than a single seamount, the system has more freedom to do unexpected things. It can move its active vent along the length of the ridge. It can produce activity in multiple locations along the structure. It can shift between vents without the eruption ending. All of these become possibilities once you accept that the underlying structure is a ridge rather than a single cone, and that is essentially what the eruption did. Within 2 weeks of the initial May 8th detection, the surface plumes were no longer coming from a single source. They were coming from 2 distinct vent areas. We will get to those 2 vents next, because what happened to them is the part of this story that has gotten less coverage and matters more than almost anything else. But before we go there, take a moment to sit with the basic situation. A volcano that nobody had on their map, in an ocean where nobody had been looking for it, erupting through a structure whose precise geometry is not known, at a depth that cannot be confirmed, with the only similar event in the recorded history of this location being a single submarine eruption 54 years ago that was itself never fully characterized. The first sentence of the eruption is that the central Bismarck Sea has a volcano that nobody knew was there. The first sentence is also the last sentence in a way, because the volcano announced itself, and then it kept going, and now it is doing things that the surface signals can only partially describe. The next thing it did was put 2 vents on the satellite images, 2.5 kilometers apart, in a configuration that almost nobody predicted. Part 3. Two vents, 2.5 kilometers apart. By the middle of May, the steam plumes coming off the central Bismarck Sea were not coming from a single point. The satellite imagery, which by then was being collected daily from NASA, the European Space Agency, and commercial providers, showed two distinct plume sources separated by approximately 2.5 kilometers of open ocean. Two plumes, two vents, one volcano. The northeastern vent was the larger of the two. The surface signature it produced, the plume base, the disturbed water around it, the thermal signal, covered an area approximately 1.5 kilometers across. That is a substantial footprint. A vent area of that size on the ocean surface implies a much smaller actual vent on the seafloor, because the surface signal spreads as the rising plume entrains and disturbs the water above it. But the footprint tells you that the energy coming out of that vent was significant. It was moving enough mass and heat to disturb a circle of ocean 1.5 kilometers wide. The southwestern vent was smaller. Its surface signature covered an area approximately 500 meters across, or about 1/3 of a mile. Still substantial for a vent at unknown depth, but visibly less energetic than the northeast vent. The two vent areas were separated by 2.5 kilometers of unbroken ocean. The plumes from each were independent. They were not branches of a single rising column. They were two distinct events happening simultaneously on the same volcanic structure. This is unusual. Most submarine eruptions documented in the modern catalogue come from a single vent. The system finds the path of least resistance, and the magma rises through it until either the eruption ends or the path becomes unstable. Eruptions with two simultaneous active vents do happen, particularly along ridge structures or fissures, but they are not the default, and when they happen, they tell you something about the underlying plumbing. They tell you that the magma supply is large enough or distributed enough to feed two pathways at once. They tell you that the structural geometry of the volcano allows two independent vents to coexist, without one overwhelming the other, and they tell you that the system has the freedom to do things that a single vent system cannot do, like shift its activity from one vent to the other while the eruption is in progress. You can think of it like a fountain with two spouts. If the water pressure is high enough, both spouts can flow at the same time. If the pressure drops, only the lower resistance spout will keep flowing. If the upper spout gets blocked, the flow shifts entirely to the lower one. The geometry of which spout is active tells you something about what is happening underneath, in the pipes. With Titan Ridge, the geometry was telling us that the volcano had a complex plumbing system, that it was capable of feeding two simultaneous pathways, and that those pathways were independent enough to be visible from space as two separate plumes. That two-vent configuration held through most of the third week of May. The northeastern vent was the dominant one throughout. It produced taller plumes, more visible discoloured water, and more pumice. The southwestern vent was steady but smaller. Both were active. Both were releasing volcanic gases. Both were contributing to the growing pumice rafts on the surface. The satellite passes from NASA's Aqua and Terra, from the Sentinel constellation, and from commercial high-resolution providers were consistent in showing the same dual-vent signature day after day, week after week. And then, around May 21st, the activity began to decrease. This is the part of the story that becomes important in retrospect. From May 21st onward, both vents started producing less surface signature. The plumes became smaller. The discoloured water became less extensive. The thermal anomalies detected by satellite instruments began trending downward. The Rabaul Volcano Observatory noted the decline in its weekly reporting. The Smithsonian Global Volcanism Program flagged the apparent quieting in its catalogue entry. If you were watching only the surface signals, the story being told was that the eruption was winding down. 2 weeks of vigorous activity, and now the system appeared to be running out of energy. That was not the story. The story being told by the surface signals was incomplete in a specific way that the next 2 weeks would make obvious. The eruption was not winding down. It was changing how it was distributing its energy. The plumes were getting smaller because the surface expressions of the eruption were getting smaller. But the underlying eruption, the gas release, the magma flux, the fragmentation of a rock at depth, was either continuing at a similar level or in retrospect increasing. How do we know that now? We know that because of what the hydroacoustic networks were picking up while the surface looked quiet. We know that because of the thermal pulse that arrived less than 2 weeks later. We know that because of the vent reorganization that came on June 1st. And we know that because of the way the plume came back, taller than it had been before. The surface signals had been filtering, and what they had been filtering was a substantial amount of the eruption. This is one of the recurring lessons of submarine volcanology, and it is worth saying out loud. The ocean is a filter. It filters what we can see from satellites. It filters what we can detect from acoustic networks. It filters what reaches the air as ash and steam. The ocean is not a transparent medium. It is a high-pressure, optically opaque, acoustically complex environment that absorbs, scatters, and redirects almost every kind of signal we use to monitor the eruptions happening at its floor. When the surface activity at Titan Ridge appeared to decrease in late May, that decrease was a real signal. But it was a signal about what the surface could detect, not about what the volcano was doing. There is a specific physics to why the surface signal can drop without the underlying eruption dropping. The plume from a submarine eruption is the result of gas-rich material rising through several hundred meters of water column. If the gas content of the erupting material changes, if the magma is releasing less dissolved gas per unit volume, the buoyancy of the plume drops, and the plume can stop reaching the surface even though the same amount of magma is being erupted. If the eruption shifts toward fragmenting more rock and less gas, the surface plume gets smaller, while the underlying rate of mass discharge can stay the same or increase. If the active vent migrates slightly along the ridge structure to a location with slightly more overlying water, the surface plume from that vent can disappear even if the vent is still active. All of those mechanisms were available to Titan Ridge during the May 21st through May 28th quiet period. We do not know which of them was operating. We probably will not know precisely, because we did not have the instruments at the vent to tell us. What we know is that whatever was suppressing the surface signal stopped suppressing it on May 28th, and what came back after that quiet week was different from what had been there before. That difference is the central editorial fact of this entire eruption. Before May 21st, the volcano was producing two distinct surface plumes from two active vents. After May 28th, the volcano was producing one surface plume from one active vent, with the underwater acoustic signature louder than it had been. The system had not paused. It had rearranged itself, and it had rearranged itself in a way that the surface monitoring caught only after the fact. But before we get to the rearrangement, we need to talk about what happened on May 22nd. Because in the middle of the apparent quiet period, the ocean floor at Titan Ridge did something else. It produced a magnitude 5.7 earthquake just north of the active vent area. Officially, it did not change the eruption. In practice, the timing is hard to dismiss. The earthquake was on the 22nd. The hydroacoustic surge started 6 days later. The thermal pulse arrived 11 days later. The vent reorganization showed up at 10 days. None of those things were officially caused by the earthquake. All of them happened in the window after the earthquake. We are going to look at that earthquake next. Part 4. The May 22nd earthquake that wasn't supposed to matter. At 20:08 UTC on May 22nd, 2026, the United States Geological Survey, the European Mediterranean Seismological Center, and the Smithsonian Global Volcanism Program all catalogued the same event. A magnitude 5.7 earthquake, located just north of the active eruption area at Titan Ridge. It was the first significant earthquake recorded in the immediate vicinity of the volcano since May 17th, and the official position on it, from every monitoring authority, was that the earthquake did not appear to change the eruption characteristics in the immediate term. That is the official position, and it is technically correct. The eruption did not suddenly intensify in the hours after the earthquake. The plumes did not get dramatically taller on May 23rd. The thermal output did not spike on May 24th. By every immediate measure available, the volcano kept doing what it had been doing, and the earthquake passed without disrupting the surface signature in a way that you could see on a satellite image. But timing is its own kind of evidence in volcanology and seismology, and the timing here is hard to dismiss completely. The earthquake was on the 22nd. The volcano was in the middle of its apparent quieting period. 6 days later, on the 28th and 29th, the hydroacoustic signals from the system surged sharply. 11 days later, on June 2nd, Mirova began detecting a strong thermal anomaly. 10 days later, on June 1st, the surface plume signature had reorganized, from 2 vents to 1. None of those changes are officially attributed to the earthquake. None of them are excluded from being influenced by it either. There is a real scientific framework for thinking about this. Large earthquakes occurring in the immediate stress field of an active volcanic system can do several things. They can redistribute static stress. They can change pore pressure conditions in the rocks surrounding the magma chamber. They can mechanically vibrate gas bubbles within rising magma, potentially encouraging coalescence and a different gas release pattern. They can affect the permeability of the vent system. They can do all of these things without producing an immediate visible response, and the response can show up in the eruption pattern weeks later, in ways that are statistically difficult to attribute to the original earthquake, even if the connection is real. The Toda, Stein, and Lin-Coulomb stress transfer framework, which is the standard tool for thinking about how one earthquake can influence the timing of subsequent events, applies to volcanic systems just as well as it does to fault systems. The framework calculates how the static stress field around an earthquake changes in 3 dimensions and identifies which neighbouring regions experience increased loading, decreased loading, or no change. The May 22nd earthquake at Titan Ridge would have produced a stress redistribution pattern in the surrounding crust and mantle that could have either increased or decreased the loading on the active magma pathway, depending on the orientation of the slip plane and the geometry of the volcanic system. We do not have that calculation for Titan Ridge. The reason we do not have it is the same reason we do not have a precise depth for the active vent. We do not have a detailed enough structural model of the system to plug into the Coulomb framework. The framework needs to know where the active fault plane is, what its orientation is, what its slip vector looks like, where the active magma pathway is, and what the local stress state is. At a well-studied volcano in a well-monitored region, all of those parameters are available. At Titan Ridge, almost none of them are. So the May 22nd earthquake sits in the catalogue as an event that officially did not change the eruption, while the timing of subsequent changes, the hydroacoustic surge, the thermal pulse, the vent reorganization, is what it is. The honest position is that the earthquake may have influenced the subsequent activity. The connection cannot be confirmed with the data available, and the temporal coincidence is suggestive but not proof. What the earthquake did demonstrate, regardless of any causal relationship with the eruption pattern, is that the region around the volcano remained under active mechanical stress. The Bismarck arc is a tectonically loaded system at baseline. The convergence rate between the South Bismarck microplate and the North Bismarck microplate along the New Britain Trench is 80 to 100 mm per year. That is a fast convergence rate, and it loads the surrounding crust at a rate that produces frequent moderate earthquakes throughout the arc. A magnitude 5.7 earthquake near an active volcanic vent is not unusual in this region. What is unusual is the proximity to a system that is in the middle of its first major eruption in 54 years. There is a second possibility worth raising, and the honest framing is that it is speculative. The earthquake could have been related to the eruption itself rather than the other way around. Magma intrusions can produce their own earthquakes as the magma cracks rock to make a pathway. The May 8th swarm that initiated the eruption was almost certainly a magma intrusion signature. If the magma supply at Titan Ridge continued to evolve through May, with new pathways opening and old ones closing, the May 22nd earthquake could have been a manifestation of that ongoing structural reorganization. Under this reading, the earthquake is not a separate event that influenced the eruption. The earthquake is the eruption, at depth, in rock, before the surface had caught up. We do not know which reading is correct. We may never know, because Titan Ridge is unlikely to receive the kind of detailed structural characterization in real time that would let us distinguish these possibilities. What we know is that the earthquake happened, that the eruption appeared quiet around it, and that within a week the surface signals began telling us the volcano had been busier than it looked. The earthquake matters for one more reason. It changes how we should read the rest of the eruption. Before May 22nd, the story being told by the data was that Titan Ridge was a routine submarine eruption in a complex tectonic setting. After May 22nd, the story being told by the data is that Titan Ridge is an active volcanic system whose surrounding crust is still under active stress and is still capable of producing significant seismic events while the eruption is in progress. That changes the hazard picture, even if it does not change the immediate forecast. A volcano in an active stress field is a volcano whose flank stability is being continuously tested. A volcano whose vent depth is uncertain, whose structural geometry has not been mapped, and whose surrounding crust just produced a magnitude 5.7 earthquake within the immediate vicinity is a volcano that warrants attention regardless of what its plume looks like on a given day. So when the hydroacoustic networks picked up the surge on May 28th, the context in which that surge arrived was a context shaped by the May 22nd earthquake. The seafloor around Titan Ridge had recently shaken. The stress field was in a different configuration than it had been before the earthquake, and the eruption, which had been apparently quieting through the previous week, was about to remind everyone that it had not actually been quieting at all. The ocean was about to tell us that, in a way only the ocean can. Part 5. When the ocean hears what we cannot see. To understand what happened on May 28th and May 29th, you need to understand how hydroacoustic monitoring works. And to understand how hydroacoustic monitoring works, you need to understand one fact about sound and water that nobody learns in school, but that turns out to matter enormously for submarine volcanology. Sound travels through water about 4.5 times faster than it travels through air. That is the simple part. The deeper part is that sound travels through water with much less attenuation than it travels through air, which means that low-frequency sounds in particular can propagate enormous distances through the ocean without losing very much of their energy. A low-frequency pulse produced by an underwater event can be detected by hydrophones thousands of kilometers away, sometimes tens of thousands of kilometers away, with enough fidelity to be analyzed for source location, source mechanism, and source intensity. This is not a small physical effect. It is the entire reason that hydroacoustic monitoring exists as a discipline. The Comprehensive Nuclear Test Ban Treaty, when it was being designed in the 90s, included a global network of hydroacoustic stations specifically to detect underwater nuclear tests. That network is still in operation today, and one of the things it turned out to be excellent at, beyond its original purpose, is detecting submarine volcanic eruptions. The same physics that lets a hydrophone 6,000 kilometers away pick up the signature of an underwater nuclear test lets the same hydrophone pick up the signature of a magma fragmentation event at the seafloor of the Bismarck Sea. The signature of a submarine volcanic eruption in hydroacoustic data is distinctive. It is not a single sharp pulse like a nuclear test would be. It is a series of lower frequency events spread over hours or days, with characteristic spectral patterns that match what you would expect from gas release, rock fracture, and pyroclastic ejection at depth. The patterns are different for different parts of the eruption. The opening of a new vent produces one signature. The collapse of a vent wall produces another. The release of a large gas bubble produces a third. Each can be characterized in the spectrogram, and skilled analysts can distinguish them. What the hydroacoustic networks monitoring the Bismarck Sea region picked up on May 28th was not subtle. The signal level rose sharply over the course of several hours, then sustained itself through the 29th at a higher level than it had been at any point since the eruption began. The pulses were more frequent. The energy per pulse was higher. The spectral pattern suggested an active vent system in vigorous eruption, not a system winding down. Whatever had been suppressing the surface signal during the previous week was not suppressing the underwater signal. The ocean was hearing the eruption at full volume even when the satellites were not seeing it. This is the mismatch that should reset your intuition about how to interpret submarine eruption updates. When you read a news article that says a submarine eruption is decreasing in intensity, what that article almost always means is that the surface visible signals, plumes, discolored water, surface thermal anomalies, are decreasing in intensity. That is a real observation, and it matters. But it is not a complete picture of the eruption. The underwater part of the eruption can be doing something completely different, and it usually requires hydroacoustic data to know. At Titan Ridge, the hydroacoustic surge of May 28th and May 29th told us several things. It told us that the eruption was not in fact winding down. It told us that the source of the surface quieting was likely a change in how the eruption was distributing its energy rather than a reduction in the total energy. It told us that the active vent system was still vigorously fragmenting magma and releasing gas. And it told us that the system was about to do something visible on the surface, because the kind of energy levels showing up in the acoustic data were not going to stay underwater indefinitely. That last prediction turned out to be correct. Within about a week of the hydroacoustic surge, the system produced the thermal pulse that Morova detected on June 3rd. Within about 10 days, the surface plumes had reorganized into the northeast dominant configuration that we'll get to in the next part. The acoustic data was leading the surface data by roughly a week, which is consistent with the timescale on which submarine eruption energy propagates from depth to the surface. The ocean was hearing the eruption before the satellites could see it. There is a broader point here about how we understand the planet. Most of the volcanic activity on Earth is happening underwater. The mid-ocean ridges alone produce more magma per year than all of the land volcanoes combined. The deep ocean basins host an unknown but substantial number of submarine volcanoes that erupt without being detected by any monitoring network. The Smithsonian Global Volcanism Program Catalogue, which is the most complete list we have, contains a few thousand volcanoes. The actual number of volcanic systems on Earth, including the ones in the deep ocean that have never been catalogued because nobody has ever detected them erupting, is almost certainly larger by an order of magnitude or more. We know this in part because the hydroacoustic networks pick up signals all the time that match the spectral signature of submarine volcanic eruptions, but cannot be matched to any catalogued volcano. The events are real. They have the right physical signature. They are coming from real locations in the ocean. They just are not coming from any volcano we know about. The standard interpretation is that there are submarine volcanoes erupting regularly in remote parts of the deep ocean that have never appeared on a satellite image because the eruption was too small to break the surface, or because cloud cover blocked the relevant satellite passes, or because nobody happened to be analysing imagery of that part of the ocean on that day. Titan Ridge is one of those volcanoes. The only difference between Titan Ridge and an uncatalogued deep ocean eruption that happened last week somewhere in the South Pacific is that Titan Ridge was vigorous enough and shallow enough to break the surface in a way that the satellites could not miss. It is not a special volcano in that sense. It is a normal submarine volcano that happened to erupt in a part of the ocean we monitor, with enough energy to be visible. There are dozens of others happening right now somewhere on Earth that we will never know about. The hydroacoustic surge of May 28th made one more thing clear. The eruption was sustained enough, energetic enough, and structurally complex enough to keep producing significant events even when the surface looked calm. That ruled out one of the more comfortable readings of the late May quieting, the reading that said the eruption was simply running out of fuel. The fuel was still there. The energy was still being released. The system had just shifted how it was expressing itself. What that shift looked like, when the surface caught up to the acoustics, was a reorganization that nobody had been forecasting. Part 6. Two vents became one. On June 1st, the satellite imagery of Titan Ridge showed something the imagery had not shown in the previous 3 weeks. The southwestern vent area, which had been steadily producing its smaller plume since mid-May, no longer carried the same plume signature. The discoloured water around it had faded. The thermal anomaly at that location had dropped. The pumice raft generation from that vent had decreased. Meanwhile, the northeastern vent area was active. Not just active, more active than it had been before. The plume from the northeast was rising higher. The thermal output was concentrating there. The pumice production was coming primarily from that single source. The volcano had reorganized itself. Two vents had become one. This is the moment in the eruption when the underlying structure made itself visible through the change in what the surface was doing. A two-vent system going to a one-vent system tells you that something has changed in the plumbing underneath, in a way that you can interpret if you know what to look for. There are two main possibilities, and they are not the same. Possibility 1 is that the system is concentrating its energy into a single pathway. Under this reading, the southwestern vent has shut down because the magma supply that was feeding it has redirected toward the northeastern vent. This can happen for several reasons. The southwestern vent could have become partially blocked by collapsed material from its own eruption, restricting the flow. The pressure conditions in the shallow magma system could have shifted in a way that made the northeastern pathway easier than the southwestern one. The magma supply itself could have changed, moving from a position where it could feed both pathways to a position where it preferentially feeds the northeast. Under any of these mechanisms, the volcano is now focusing its output. The total energy in the system is being delivered through a single vent instead of two. The northeastern vent is doing the work of both vents at once. This reading has implications. A single vent eruption delivering the total energy that was previously distributed across two vents is, by definition, a more energetic single vent eruption than either of the original vents would have been alone. The thermal output should be higher, the plume should be taller, the pumice production should be more concentrated, the hydroacoustic signal from the active vent should be louder. The eruption is not slowing down, it is sharpening. This reading is consistent with what the surface signals showed after June 1st. The mirror thermal pulse of 201 megawatts on June 3rd came from a single source. The plume rose to 5 kilometers above sea level, which is taller than either of the original two-vent plumes had reached. The pumice rafts continued to grow. The hydroacoustic signal stayed elevated. Everything that the focusing pathway interpretation would predict, the data showed. But there is a second possibility, and it is not exclusive of the first. The southwestern vent might not have shut down at all. It might still be active. It might be producing the same magma flux as before, or even more. But the surface signature of that vent, the part the satellites can detect, might have changed in a way that makes it look quieter when it is not. There are several mechanisms that can produce this kind of false quieting. The vent might have migrated slightly along the ridge structure to a deeper location, where the additional water pressure suppresses the surface plume, even though the underlying eruption continues. The eruption character at that vent might have shifted toward lower gas content, the same amount of magma being erupted, but with less dissolved volatile to produce a buoyant plume. The fragmentation pattern might have changed so that less material reaches the upper water column. Under any of these mechanisms, the southwestern vent is still part of the eruption. It just is not showing up on the satellite images the way it was. This second reading is harder to verify, because it depends on signals that we mostly cannot measure. We would need to know whether the southwestern vent is still producing acoustic energy at the level it was. We would need to know whether the magma flux at that location is the same as before. We would need a high-resolution map of the seafloor at the active region to see whether the vent has migrated. We do not have any of those things in real time. So the second reading is plausible, but it is not directly observable. The honest position is that both readings are physically viable, and the truth is probably some combination of the two. The northeastern vent is genuinely doing more work than it was before. The southwestern vent has probably reduced its activity in some way, but may not have shut down completely. The system as a whole is reorganized in a way that the surface signature reflects, but the underlying eruption is more complex than the surface signature alone can tell us. What matters editorially is what this reorganization means for the danger profile of the system, and the answer is that it depends on the depth. Again, we are back at the depth question, and we will keep coming back to it, because every interpretation of the eruption routes through it. If the active northeastern vent is at the deeper end of the estimated depth range, say 600 meters below sea level, then the focusing of energy into a single vent does not necessarily increase the surface hazard, because the additional water column continues to suppress the most violent expressions of the eruption. The eruption can be more energetic underwater without being more dangerous above water. If the active northeastern vent is at the shallower end, say 400 meters below sea level, then the focusing of energy into a single vent does increase the surface hazard, because the suppressing effect of the overlying water is less complete. More energy reaching the surface means more potential for violent steam-magma interactions, taller plumes, larger pumice generation, and more frequent ash-rich eruption events. If the active northeastern vent has built itself up a cone of pumice and pyroclastic material since the eruption began, which is geometrically plausible given a month of continuous activity, then the effective vent depth is shallower than wherever the original vent started, because the apex of the cone is closer to the surface than the original seafloor location of the vent. As the cone grows, the depth decreases. As the depth decreases, the explosivity profile shifts. This is the mechanism by which submarine volcanoes can become more dangerous over the course of a single eruption, even when the underlying magma supply is constant. The June 4th plume, reaching 5 kilometers above sea level, is consistent with all three of these possibilities. We cannot use the plume height alone to distinguish them. What we can say is that the system is producing surface activity at a level that requires either a moderately energetic eruption at depth, or a less energetic eruption at shallower depth, or some combination. None of those readings is comforting. The vent reorganization on June 1st changed the editorial picture for Titan Ridge in one specific way. Before June 1st, the system was a two-vent eruption that was apparently winding down. After June 1st, the system was a one-vent eruption that was visibly intensifying. The story that the data was telling shifted from "this might be ending soon" to "this is in a new phase," and we do not know how long the new phase will last. 2 days later, on June 3rd, the Mirova system would record a thermal output that confirmed the new phase was not a brief pulse, but a sustained escalation, 201 megawatts, from a volcano that was supposedly going quiet 10 days earlier. Part 7. 201 megawatts. The Middle Infrared Observation of Volcanic Activity System, known by its acronym Mirova, is a satellite-based thermal monitoring system jointly operated by the Universities of Turin and Florence in Italy. The system uses thermal infrared imagery collected by the MODIS instruments on NASA's Aqua and Terra satellites, supplemented by data from the European Space Agency's Sentinel constellation, to detect and quantify the thermal output of volcanoes worldwide. It runs continuously, it produces near real-time updates on its public dashboard, and it is the gold standard for satellite-based volcanic thermal monitoring. Moreover classifies volcanic thermal output into power categories. Below 100 megawatts, the system flags the output as low to moderate. Between 100 and 1000 megawatts, the classification shifts to high. Between 1000 and 10,000 megawatts, the classification is very high. Above 10,000 megawatts is the extreme category. These thresholds are not arbitrary. They correspond to physically meaningful regimes of volcanic activity, from background hydrothermal output through routine eruptive activity, up to the most energetic events that satellite thermal instruments can characterize. In the first 3 weeks of the Titan Ridge eruption, moreover detections were moderate. The thermal output of the system, integrated over the active surface area, peaked at approximately 96 megawatts on the more active days, and ran lower than that on the days when surface activity was suppressed. 96 megawatts is not a small number. It is substantial volcanic thermal output, but it sits below the high classification boundary. The system was producing enough heat to be reliably detected, but not enough to cross into the high category. That changed on June 3rd. At 10:40 UTC on June 3rd, moreover recorded a combined detection from MODIS and Sentinel data, showing a thermal output of approximately 201 megawatts from the active vent area at Titan Ridge. 201 megawatts, more than double the prior peak. Solidly into the high classification category, the single largest thermal pulse the system had produced since the eruption began. To put 201 megawatts of thermal output into context, consider what that number represents. The thermal output of a single megawatt is roughly the power consumption of a small town. 201 megawatts is roughly the thermal output of a moderate-sized power plant, enough to provide electrical power for a small city. And that output is being measured at the surface of the ocean, after passing through hundreds of meters of seawater that absorbs and scatters most thermal energy before it reaches the upper layers where satellites can detect it. The actual heat being generated at the active vent at depth is meaningfully larger than the 201 megawatts that reach the surface measurement. We do not know by how much, because we do not know the depth, and we do not know the efficiency of the heat transfer through the intervening water column. What we know is that whatever is happening at the vent is producing enough thermal energy to make 200 megawatts visible from orbit. For comparison, the thermal output of Kilauea during its current eruption episode at the summit caldera typically runs in the range of several tens to several hundreds of megawatts, depending on whether fountaining is active and on the satellite pass timing. The thermal output of Mayon in the Philippines during its current activity has run in the tens to low hundreds of megawatts. The thermal output of Sangay in Ecuador, which has been in nearly continuous eruption for years, runs in the high hundreds to low thousands of megawatts on its most active days. 201 megawatts at Titan Ridge places the system in the company of major actively erupting volcanoes worldwide. The notable difference is that we can see the lava lake at Kilauea, we can put cameras on the rim at Mayon, we can watch Sangay erupt in real time from a number of monitoring stations on the surrounding terrain. We cannot do any of those things at Titan Ridge. The 200 megawatts is happening somewhere underneath several hundred meters of dark water, and the only window we have into it is the thermal signal reaching the ocean surface. The June 3rd pulse came with companion observations that helped contextualize what was happening. On the same day, the Darwin Volcanic Ash Advisory Center issued an advisory noting ash and steam plumes from the system, reaching approximately 12,000 feet, or roughly 3,660 meters, above sea level. That is a substantial plume. A submarine volcanic plume reaching 12,000 feet implies that the eruption is energetic enough to push gas and fine ash through several hundred meters of water column and several additional 1,000 meters of atmosphere before losing its buoyancy. That is the kind of plume height that disrupts aviation, that drifts downwind for hundreds of kilometers, and that delivers fine particulate matter to populated areas in the path of the prevailing winds. By the following day, June 4th, the plume height had nearly doubled. Observations from the same VAAC and from independent satellite analyses placed the plume at approximately 5 kilometers above sea level, about 16,400 feet. 5 kilometers of plume from an underwater volcano whose active vent is at unknown depth. That is the part that should sit with you for a moment. 5 kilometers of vertical extent, through hundreds of meters of water, then through several thousand meters of atmosphere. The buoyancy required to drive a plume that tall, given the suppressing effects of the water column above the vent, is significant. The eruption was either at the shallower end of the estimated depth range, or supplied with very high gas content, or experiencing a sharp pulse of magmatic energy that briefly overcame the suppressing effects of the overlying water. Probably some combination. The thermal record after June 3rd has been pulsing. By the most recent updates available, the Mirova detections have dropped back towards single-digit megawatts during some satellite passes, while still showing elevated levels on others. This pulsing pattern is the diagnostic signal that matters more than any single peak number. A volcano that produces a thermal output of 201 megawatts and then settles back to 2 megawatts is not a volcano whose eruption is over. It is a volcano whose eruption is releasing energy in pulses rather than steadily. The satellite measurement captures the thermal output at the moment of the pass. If the pass coincides with a high output pulse, you get 200 megawatts. If it coincides with a quiet interval between pulses, you get 2. Both numbers are real measurements of the volcano at the moment of the pass. Neither is the true average output. The true average is somewhere between them, and to know exactly where, you would need continuous monitoring instead of satellite snapshots. This is one of the recurring lessons of Mirova data, and it applies generally to all satellite-based volcano thermal monitoring. The thermal signal varies on timescales much shorter than the satellite revisit interval. A polar orbiting satellite passes over a given location once or twice a day. A volcano in active eruption can change its thermal output on timescales of minutes to hours. The satellite catches whatever is happening at that location during the few minutes of the pass, and that snapshot is all you get until the next pass. When the snapshot is high, the high number reflects something real. When the snapshot is low, the low number reflects something real too. But neither snapshot tells you what the volcano was doing in the hours between passes. The honest reading of the post-June 3rd thermal data at Titan Ridge is that the eruption is in a pulsing regime. It is producing intermittent strong pulses interspersed with quieter intervals. The strong pulses are reaching the high classification threshold, the quiet intervals are not. The overall average output is somewhere in the moderate to high range, probably integrated over a meaningful surface area of active venting. The volcano is doing real volcanological work. It is not winding down, it is breathing. And while it breathes, the plume keeps reaching the sky, 5 kilometers up, visible from orbit, tracked by aviation authorities, drifting downwind from a point in the central Bismarck Sea that nobody mapped before May 8th, fed by a vent at a depth nobody can confirm, in a system that has now been actively erupting for nearly a month with no signs of ending. How does a volcano whose vent is supposed to be several hundred meters underwater produce a plume that reaches 5 kilometers above sea level? That question turns out to be its own kind of evidence, and the answer takes us to one of the central physical puzzles of this eruption. Part 8. 5 kilometers above the sea. A column of seawater exerts pressure on whatever is underneath it. The pressure is roughly 1 atmosphere, 1 bar, for every 10 meters of depth. At a depth of 500 meters, the pressure on the seafloor is approximately 50 atmospheres. At 600 meters, it is approximately 60 atmospheres. These are not small numbers. 60 atmospheres of pressure is enough to suppress most kinds of explosive expansion. It is enough to keep dissolved gases in solution that would otherwise vigorously exsolve at lower pressures. It is enough to fundamentally change how an erupting magma releases its energy compared to the same magma erupting at the surface. So when a submarine eruption produces a plume that reaches 5 kilometers above sea level, there is a physical puzzle to explain. The pressure conditions at the vent should be suppressing exactly the kind of energetic gas release that produces tall plumes. The fact that material is reaching the surface as a tall plume and then continuing to rise into the atmosphere as a coherent column means that something is overcoming the suppressing effect of the overlying water. There are a few different things that can be that something, and identifying which one applies at Titan Ridge tells us something about what kind of system we are dealing with. Option 1 is that the vent is shallower than the estimates suggest. If the active vent at Titan Ridge is at 300 meters depth instead of 500, the overlying pressure is roughly 30 atmospheres instead of 50. That is still substantial, but it is meaningfully less restrictive, and a magma with high gas content can begin to vigorously exsolve at that pressure in a way that it cannot at 50 atmospheres. A shallower vent produces a more energetic surface expression. The 5-kilometer plume is consistent with a shallower vent. This option is consistent with another physical fact about the eruption. The pumice rafts at Titan Ridge have been substantial, covering more than 69 square kilometers by late May, with bands extending up to 200 kilometers from the source. Pumice forms when gas-rich magma is rapidly depressurized, allowing dissolved volatiles to exsolve and expand within the cooling melt. The pumice that has been generated at Titan Ridge tells us the eruption is gas-rich, and the depressurization is sufficient to produce extensive vesiculation. Both of those characteristics are easier to achieve at shallower depths. The pumice volume is at least suggestive evidence that the active vent is not at the deepest end of the estimated range. Option 2 is that the eruption is supplying very high volumes of gas per unit mass of erupted magma. Some basaltic and basaltic andesite magmas can carry several weight % of dissolved volatiles, primarily water and carbon dioxide. When those gases exsolve, they expand explosively. If the magma at Titan Ridge is unusually gas-rich, then even at a depth that would normally suppress vigorous eruption, the gas overpressure could be sufficient to drive material through the water column and into the atmosphere. The 5-kilometer plume is consistent with high gas magma at moderate depth. We do not know the composition of the magma at Titan Ridge directly. We have not analysed any of the pumice from the rafts in detail at the time of writing. We can infer from the regional geology that the magma is probably basaltic to basaltic andesite, consistent with the volcanism of the broader Bismarck Arc and the New Britain volcanic chain. Whether the specific source at Titan Ridge is unusually volatile rich is an open question. The pumice analysis, when it eventually happens, will likely give us some answers. Option 3 is that the eruption is currently going through a particularly energetic pulse. The June 3rd thermal pulse and the June 4th plume height occurred together, which is consistent with an unusually energetic phase of the eruption, rather than a steady-state behaviour. Under this reading, the volcano is producing a tall plume during the pulse because the pulse is delivering extra energy, and the surface expression in quieter intervals between pulses is more consistent with what we would expect from a deep event. The plume height in this case is a measurement of the peak energy rather than the average. Option 4, and this is the one that connects back to the depth question in the most concerning way, is that the active vent has been progressively becoming shallower over the course of the eruption, because the eruption itself is building a cone of pumice, pyroclastic material, and rock fragments on the seafloor. Submarine cones built from loose volcanic material are a well-documented feature of sustained submarine eruptions. The cone grows as material is deposited around the active vent. The apex of the cone gets closer to the sea surface over time. The effective vent depth, the depth from which the eruption is actually escaping into the water column, decreases. As the effective depth decreases, the suppressing effect of the overlying water decreases, and the surface expression of the eruption becomes more energetic. Under this reading, the Titan Ridge eruption started at one depth, and is currently erupting at a meaningfully shallower depth because of the cone it has built. The 5-kilometer plume reflects the current shallower effective depth, not the original vent depth. The trajectory of the eruption is toward progressively shallower effective depth as the cone continues to grow, which means the surface expressions of the eruption are likely to continue intensifying as long as the magma supply continues. And in the limit, if the cone grows enough to reach the surface, the volcano builds an island. This is exactly the mechanism by which submarine volcanoes have built new islands throughout geological time and through historical time. Surtsey off Iceland built itself this way in 1963. Anak Krakatau in Indonesia built itself this way. Hunga Tonga Hunga Ha'apai built itself this way before the 2022 eruption. The mechanism is not exotic. It is one of the most common processes by which the planet creates new land. Whether Titan Ridge is currently on that trajectory is something we cannot confirm in real time, because we cannot map the active vent area at the resolution required to see the cone. We can infer from the pumice volume and the eruption duration that some cone construction is probably happening. We cannot quantify it. We cannot project it forward. What we can say is that the option 4 reading is physically plausible and consistent with the observed escalation in the surface signals, including the 5-kilometer plume. The combination of these 4 options is probably what is happening. The vent is likely somewhere in the middle of the estimated depth range. The magma is likely moderately gas-rich. The eruption is in a pulsing regime where some pulses are more energetic than others, and a cone is likely being constructed on the seafloor that is gradually reducing the effective vent depth. All 4 mechanisms are contributing to the observed 5-kilometer plume. Each one is harder to confirm in real time than the next. What you should take away from this physical discussion is that a 5-kilometer plume from an underwater volcano, whose vent depth we cannot confirm, is consistent with several different physical regimes, and the system is probably in some combination of them at any given time. The plume height does not tell us a single clean fact about the eruption. It tells us that the eruption is energetic enough to overcome the suppressing effect of the overlying water at some level, and that the volcano has more than one way of being energetic. The volcano is producing real volcanological work. The work is being delivered through processes we can characterize physically, but cannot map directly. The system is in active eruption. The eruption is escalating by some measures. The escalation is happening underneath a layer of seawater whose exact depth we do not know. And that brings us back to the question that controls every interpretation in this video. We have been circling it from the beginning. We have alluded to it in every part. We have pointed at it again and again. Now we need to land on it directly, because everything we have walked through up to this point, the timeline, the vent reorganization, the hydroacoustic surge, the thermal pulse, the 5-kilometer plume, funnels into a single sentence about what we do not know. We do not know how deep the vent is. Part 9. The depth. We do not know. There is a number floating around in the reporting about Titan Ridge that you should be careful with. The number is 500 to 600 meters, and it is the depth that some early reports have given for the active vent. The number is not wrong exactly. It is an estimate derived from a combination of older bathymetric data over the broader Titan Ridge structure, inferences from the surface signal characteristics, and reasonable physical assumptions about where a vent of this productivity would have to be located, given what the satellites are detecting. It is a useful working estimate. It is also, importantly, not confirmed. NASA's Earth Observatory has stated this openly. The Smithsonian Global Volcanism Program has stated this openly. The Rabaul Volcano Observatory has been careful in its communications to characterize the depth as uncertain rather than known. The reason all three institutions have been careful is the same reason. Nobody has conducted a high-resolution bathymetric survey of the actively erupting structure at Titan Ridge recently enough to characterize the precise depth of the active vent or vents. The estimates of 500 to 600 meters are inferences from indirect data. They could be right. They could be off by 100 meters in either direction. They could be off by more. I want to be precise about why this matters, because it sounds technical, and it is actually the central editorial fact of this entire eruption. Depth controls explosivity. We have walked through this physics already. The pressure of the overlying water column suppresses the vigorous gas exsolution that produces explosive eruption. At greater depth, the suppression is more complete. At lesser depth, the suppression is less complete. A vent at 1500 meters is in a fundamentally different regime than a vent at 150 meters. The same magma, with the same composition, erupting at the same rate, produces a fundamentally different eruption depending on which side of those depth boundaries it is on. We have an estimated range for Titan Ridge that straddles a meaningful boundary, and we cannot confirm which side of that boundary the vent is actually on. Depth controls plume dynamics. A plume rising from a deep vent has to traverse more water column before reaching the surface. It loses more energy to entrainment and mixing on the way up. The mass of the plume that reaches the surface, as a fraction of the mass leaving the vent, is smaller at greater depth. A plume from a shallower vent retains more of its initial energy. The 5-kilometer plume at Titan Ridge is consistent with multiple depth assumptions, as we discussed, but it would tell us something more specific if we knew the depth. Without the depth, the plume tells us only that the system is producing energetic surface expression somehow. Depth controls steam-magma interaction. When magma erupts at depth, the surrounding seawater is under high pressure and elevated temperature. The interactions between magma and water are dominated by gradual heat transfer rather than explosive flashing. When magma erupts at shallower depth, the seawater can flash to steam much more violently. The eruption character shifts from effusive to phreatomagmatic. Phreatomagmatic eruptions are characterized by sharp pressure pulses, intense fragmentation, and the production of fine ash-sized material rather than larger fragments. They are also more dangerous. They produce sudden energetic surface expressions that can include rapid changes in plume height, acoustic shock waves at the surface, and in extreme cases, the kind of basal flows and surface displacement that produced the Hunga Tonga atmospheric pressure waves in 2022. Depth controls cone stability. A cone built from loose volcanic material at depth is stabilized to some extent by the surrounding water pressure. The same cone at shallower depth has less hydrostatic support and is more prone to flank collapse, particularly if undercut by its own erosion or if subjected to seismic shaking. A submarine cone that grows to shallow depth becomes a different category of structure than the same cone at greater depth. It becomes more capable of producing the kind of partial collapse that generates a local tsunami. That is a transition we cannot project without knowing the current depth and the rate of cone growth. Depth controls tsunami potential. Submarine eruptions can generate tsunamis through several mechanisms, and the relative importance of each mechanism depends strongly on depth. At greater depth, the dominant tsunami generation mechanism is volume displacement from the erupting plume. This is generally a relatively small effect for moderate eruptions. At shallower depth, additional mechanisms become available. Phreatomagmatic explosions can displace water directly. Surface waves can be coupled into the eruption column, and cone collapse can move material on a scale that produces meaningful run-ups. The progression from a deep vent that cannot generate a significant tsunami to a shallow vent that can is not a smooth function of depth. It is a transition that happens over a range of depths and depends on the specific eruption regime. Titan Ridge is somewhere in that range. We do not know where. This is the central editorial fact. Every hazard outcome at Titan Ridge, the explosivity, the plume behavior, the cone stability, the tsunami potential, depends on the depth of the active vent. We have an estimated range. We do not have a confirmed depth. The uncertainty in the depth is not a side issue. It is the main issue. The volcano is being monitored through indirect signals, and the most important physical parameter that would let us interpret those signals is unknown to within several hundred meters. I want to address one possible reading of this that you should reject. The reading is, scientists are hiding the depth. They know the depth, they just are not telling us. This reading is incorrect, and the reason it is incorrect is the same reason we keep coming back to. The data is openly published. The Smithsonian Global Volcanism Program entry for the Central Bismarck Sea volcano, classified under catalogue number VN equals 250030, is publicly accessible. The Mirror dashboard publishes the thermal anomaly data in near real time. The Darwin VAAC advisories are issued for public aviation use. NASA's Earth Observatory has published a detailed article on the eruption, with the depth uncertainty stated explicitly. The Rabaul Volcano Observatory issues regular bulletins. Geomar in Germany has confirmed the eruption independently. The amount of public data on this eruption is substantial. The absence of a confirmed depth is not concealment. It is the actual state of knowledge. The reason for the actual state of knowledge is logistical. High-resolution bathymetric mapping of an active submarine eruption site requires either an autonomous underwater vehicle, a research ship with a multi-beam sonar system, or both. Either option requires substantial time, funding, planning, and equipment. The central Bismarck Sea is a remote location. There is no rapid deployment capability for submarine bathymetric surveys in this part of the world. The mapping that exists for the broader area is older, lower resolution, and was not designed to characterize a specific actively erupting vent. To get a high-resolution map of the current active vent, you would need to schedule a dedicated research mission, fund it, equip the ship, sail it from wherever it is to the central Bismarck Sea, and conduct the survey while the eruption is in progress. That is a real possibility for the coming weeks or months. It is not something that can be done overnight. So the depth is uncertain because of logistics, not because of conspiracy, not because of suppression. Because mapping the seafloor is hard, mapping the active seafloor during an eruption is harder, and mapping it in a remote part of the Pacific is harder still. The honest position is that the uncertainty is real, and the explanation for the uncertainty is real, and the implications of the uncertainty are real. Let me give you one more way of thinking about why the depth question is the central question. If you were trying to characterize a fire in a building, the difference between a fire in the basement and a fire on the top floor matters enormously, even if the fire itself is producing the same amount of smoke at the windows. The basement fire is going to behave differently in terms of how the building structure responds, where the fire can spread, what the rescue options look like, and what the failure modes are. The top floor fire is a different problem entirely. Same fire, same fuel, different position, different consequences. We can see the smoke at the windows of the Titan Ridge building. We cannot see which floor the fire is on. The smoke is consistent with the fire being on several different floors. Until we know which floor it is on, we cannot fully assess what the building is about to do. The Hampton-Lee-Locat empirical framework that we will discuss in the Ritter Island context applies the same logic to submarine collapse tsunamis. The same volume of material collapsing into the ocean produces a meaningfully different run-up at adjacent coasts depending on the depth at which the collapse originates. Shallow collapses produce big tsunamis. Deep collapses produce smaller ones, with the run-up falling off roughly with depth. The current best estimate of Titan Ridge's vent depth is right in the middle of the range where the framework's predictions change most rapidly. A few hundred meters of difference in depth changes the predicted run-up by a factor of 2 or more. That is not a small uncertainty. That is the difference between a coastal village being inundated and a coastal village being safe. And the depth is not the only thing we do not know. We do not know the precise rate at which the cone is being constructed, if a cone is being constructed at all. We do not know the gas content of the magma. We do not know the temperature of the erupting material at the vent. We do not know the precise geometry of the conduit system that connects the surface vent to the deeper magma reservoir. We do not know whether there are additional vents along the Titan Ridge structure that are currently inactive but capable of opening. Each of these uncertainties compounds the others. Each of them widens the confidence interval around any forecast we try to make about where the eruption is going next. And the implications are what bring us to the next part of the story. Because while scientists are watching Titan Ridge through indirect signals, the eruption is producing direct effects on the people who live within reach of it. The pumice that has been building up in the rafts has started arriving on the shores of the Admiralty Islands. The fishermen who work the waters around Manus Island have been dealing with floating volcanic rock for weeks. The acoustic signals that the hydroacoustic networks were picking up, those same signals were producing local sensory reports from people on the islands. The volcano is not abstract. It is producing real effects on real people in real places. And those effects are some of the most direct evidence we have about what the eruption is actually doing underneath all that uncertainty. Part 10. Pumice on the shore. The first pumice rafts from Titan Ridge appeared on satellite imagery within days of the May 8th detection. By May 15th, the rafts were extensive enough to be tracked as distinct features on the standard satellite passes. By May 25th, pumice rafts covering more than 69 square kilometers were visible to the west of the eruption site, with bands of floating volcanic rock extending up to 200 kilometers from the source. The numbers are the kind of numbers that sound abstract until you remember what they describe. 69 square kilometers is roughly the surface area of Manhattan. 200 kilometers is roughly the distance from New York City to Philadelphia. The volcano has been producing enough pumice for the floating rafts to cover an area the size of a major city, and to drift in continuous bands for distances equivalent to traveling between 2 American metropolitan areas. The Rabaul Volcano Observatory began issuing maritime advisories shortly after the rafts became extensive. The advisories told vessels to avoid the pumice raft zones. The reason is practical. Pumice is volcanic rock that has been so thoroughly filled with small gas bubbles during cooling that its bulk density is less than the density of water. It floats, but it is still rock. It is hard enough to scratch and damage metal hulls. It is dense enough as a packed raft to fill a small boat's intake systems. It can foul fishing nets in ways that make the nets difficult or impossible to retrieve. It can clog the cooling systems of small marine engines. The same engineering challenge that volcanic ash poses to jet engines. Fine, hard, abrasive particles entering systems that were not designed for them. Pumice rafts pose to small boats. The fishing communities in the Admiralty Islands have been dealing with this for weeks. Their working knowledge of the local ocean is one of the most direct sources of information we have about the eruption. The Bismarck Sea is not a recreational ocean. It is a working ocean. People fish here for food and for livelihood. The arrival of extensive pumice rafts in their working waters has produced concrete economic and operational disruption. Boats have had to alter routes. Fishing has had to be done in different locations. The maritime authorities have had to issue and update advisories as the rafts have drifted. The local accounts of the eruption from earlier in its history are striking. People near the Admiralty Islands have described the eruption, in its more active phases, as sounding like thunder. The sea air, near the eruption zone, has been described as smelling like burning metal. Both of those sensory descriptions are consistent with the underlying chemistry of an eruption like this one. Thunder-like sounds from a submarine eruption can be produced by gas releases at the vent that propagate as low-frequency pressure waves through the water and then into the air. The burning metal smell is consistent with high sulfur dioxide flux from the vent reacting with seawater. Sulfur compounds in the gas phase can produce exactly the kind of acrid, metallic-tasting odor that people are reporting. The sensory descriptions are not casual atmospheric impressions. They are diagnostic signatures of a real submarine eruption, processed through the senses of people who happen to be downwind of the vent. In the most recent phase of the eruption, after the June 1st vent reorganization and the June 3rd thermal pulse, the pumice production has continued. New material has been added to the existing rafts. Currents in the Bismarck Sea have begun moving the rafts toward the coastlines of the Admiralty Islands. As of the past several days, pumice has been arriving on the shores of inhabited islands in the Admiralty Group. This is the eruption reaching people directly, not through abstract satellite imagery, but through physical material on the beach, in the surf zone, washing up on the rocks where people walk and fish. The arrival of pumice on inhabited shores is one of the most direct measures of the eruption's reach. It tells you that the volcano is producing not just a brief pulse of material, but a sustained output, that the output is being conveyed efficiently across more than 100 kilometers of ocean by currents, and that the people in the path of the rafts are now part of the eruption's footprint, whether they were ready for that or not. Pumice on the shore is not dangerous in the way ash from a land volcano is dangerous. It does not cover crops, it does not collapse roofs, it does not block roads, but it changes the use of the coastline, it impedes boats, it marks the beach with a layer of strange, light, gas-pocked volcanic rock that came from a volcano nobody knew was there a month ago. And it tells you that the eruption is real, sustained, and producing real-world material at a real-world rate. There is a useful comparison here to the Hunga Tonga eruption in 2022. Hunga Tonga produced enormous pumice rafts that drifted across the South Pacific for over a year, eventually washing up on beaches across Australia, New Zealand, Fiji, and other Pacific nations. The Hunga Tonga rafts were a sustained presence in the ocean for months, in a way that became part of the documented memory of the eruption. The Titan Ridge rafts are not at the Hunga Tonga scale. The Hunga Tonga eruption was orders of magnitude more energetic, and the Pumice volume reflected that. But the underlying physical phenomenon is the same. A submarine eruption that produces gas-rich magma at sufficient volume creates floating volcanic rock that drifts on the surface of the ocean for as long as the rock can resist being saturated and sinking. The Titan Ridge rafts are durable enough to have already persisted for nearly a month, and to have drifted hundreds of kilometers. They will likely continue to be a presence in the Bismarck Sea for some time after the eruption ends. The connection back to the central depth question is important here. The volume of pumice that an eruption can produce depends, among other things, on the gas content of the erupting magma and on the depth at which the eruption is occurring. Gas-rich magma at moderate depth produces extensive pumice. Gas-poor magma at the same depth produces much less. Deeper eruptions tend to produce less pumice because the suppressing effect of the overlying water reduces the gas exsolution that creates the vesicular structure of pumice. The fact that Titan Ridge has produced 69 square kilometers of pumice rafts and continues to produce more is suggestive evidence that the eruption is gas-rich and that the vent is not at the deepest end of the estimated depth range. It does not nail down the depth. But it tells you the eruption has the kind of energy profile that produces substantial pumice, and it tells you that the depth is consistent with that energy profile. The fishermen who are working the waters around the Admiralty Islands are not reading these signals as physics. They are reading them as practical conditions affecting their work. But the signals they are reading are the same signals the satellites are detecting and the hydroacoustic networks are recording. They are just being measured by different instruments. The fishermen feel the eruption through the changes in their fishing grounds, through the floating rock that fouls their nets, through the smell of burning metal carried on the wind off the eruption zone, through the thunder-like sounds that reached them when the eruption was at its loudest. The satellites measure the same eruption through thermal anomalies and plume heights and surface water discoloration. The hydroacoustic networks measure it through low-frequency pressure waves propagating through the deep ocean. All of these instruments are pointing at the same underwater event. None of them, alone, is enough. Together they build a picture that is detailed but still incomplete in the one place where it most needs to be detailed, at the depth of the active vent. And while the volcano keeps signalling to us through every channel it can, through the rafts on the shore and the plumes in the sky and the sounds in the water, there is one thing the volcano is not signalling clearly enough for us to read: the depth that controls how much more pumice is coming, how much taller the next plume might be, and whether the cone being built on the seafloor will eventually become unstable enough to slide. That depth is still hidden, and it is still the question. There is one other reason this depth question matters for the people on the Admiralty Islands. 200 kilometers south of Titan Ridge, in 1888, a submarine volcanic structure called Ritter Island did exactly the thing that the depth question is asking about. It collapsed, and the collapse generated a tsunami that killed several hundred people on the islands adjacent to it. The history of the Bismarck Arc is part of why Titan Ridge is being watched the way it is. Part 11. Ritter Island was 200 kilometers away. On the morning of March 13th, 1888, a volcanic island in the southern Bismarck Arc collapsed. The collapse was not a slow process. It was sudden. Part of the volcanic edifice of Ritter Island gave way and slid into the surrounding water as a debris avalanche moving at approximately 40 meters per second. The volume of material involved was approximately 4.6 cubic kilometers. The damage propagated approximately 600 kilometers across the region. The tsunami generated by the displaced water reached the adjacent islands of Umboy, Saka and West New Britain, with run-up heights ranging from 15 meters to 50 meters. Several hundred people were killed. The event is documented in the historical record and reconstructed in the modern volcanological literature, most thoroughly in a 2008 paper by Silver and colleagues in the Journal of Volcanology and Geothermal Research, which catalogued 12 distinct flank collapse debris fans across the broader Bismarck volcanic arc. Ritter Island sits approximately 200 kilometers south of where Titan Ridge is currently erupting. It is in the same volcanic arc system. The South Bismarck microplate and the North Bismarck microplate convergence that drives volcanism at Titan Ridge is the same convergence that drove volcanism at Ritter Island. The geology, the tectonic setting, and the general style of volcanism are continuous across these two locations. The Bismarck Arc has a documented history of producing flank collapse events. Ritter Island is the best-known example, but it is not the only one. The Silver catalogue of 12 debris fans across the arc, each with footprint areas ranging from 20 to 150 square kilometers, demonstrates that flank collapse is a recurring mode of volcanic behavior in this arc system, not an aberration. I want to be careful with this comparison, because the temptation when you bring up an event like Ritter Island is to suggest that the same thing is about to happen at Titan Ridge. That is not what the data supports. Ritter Island in 1888 was a different kind of structure than Titan Ridge is right now. Ritter was an island-building volcano whose subaerial edifice had been growing for centuries, with steep flanks that had reached the kind of geometry where they could fail catastrophically. Titan Ridge is currently a submarine system that may or may not be building a cone, that may or may not be at the depth where flank failure becomes a real concern. The two systems are not at the same stage of their development, and the immediate hazard profiles are not equivalent. What Ritter Island demonstrates is that flank collapse from a volcanic structure in this arc is a documented historical mechanism, that it can produce significant tsunamis, and that the run-ups can be devastating to the immediately adjacent islands. The mechanism is real, and the precedent is local. Whether the mechanism applies to Titan Ridge depends on what Titan Ridge is actually doing underneath the water, which is the question we keep returning to and cannot definitively answer. There is a physical framework called the Hampton-Lee-Locat empirical relationship that helps think about how the depth of a submarine collapse affects the resulting tsunami run-up. The framework is a rough approximation derived from a combination of historical case studies and physical modelling. It says very approximately that doubling the depth at which the collapse originates roughly halves the run-up that the resulting tsunami produces at adjacent coasts. The relationship is not exact. It depends on the volume of material involved, the geometry of the collapse, the bathymetry of the surrounding seafloor, and the orientation of the failure relative to the nearest coast. But as a rough guide, depth matters a lot. If we apply this framework hypothetically to Titan Ridge, and the emphasis is on hypothetically, because we do not know that any collapse is imminent or even likely, the depth uncertainty translates directly into uncertainty about the potential run-up. Ritter Island's collapse originated near the surface, which is why the run-ups it produced were so large. A hypothetical comparable volume collapse at Titan Ridge, originating at 5 to 600 meters depth, would be expected to produce run-ups in the range of approximately 8 to 25 meters at the closest adjacent coasts, based on the Hampton-Lee-Locat scaling. That is a smaller range than Ritter Island produced, but it is not a small range. 8 meters of run-up is enough to inundate low-lying coastal villages. 25 meters of run-up is enough to seriously damage substantial coastal infrastructure, and these are estimates based on assumed depth and assumed volume. both of which are uncertain. I cannot stress enough that this is a worst-case framework calculation, not a forecast. The probability that Titan Ridge produces a Richter-scale collapse in the immediate future is not high. The volcano has not built a subaerial edifice. It is not at the kind of structural maturity where catastrophic flank failure is a likely event. The current activity does not show the indicators that would suggest imminent collapse. But the depth uncertainty means we cannot rule out a hypothetical collapse, and the volume uncertainty means we cannot estimate the consequences with precision. The combination of those uncertainties is what makes Titan Ridge worth attention, beyond what its current activity alone would warrant. Ritter Island also demonstrates something else about how submarine volcanic hazards have been understood historically. For most of the 20th century, the dominant model of tsunamis treated them primarily as earthquake-driven phenomena. The standard warning system that the Pacific Basin has been operating since the 1950s was designed primarily for earthquake-generated tsunamis, with sensors and detection algorithms tuned to that physical mechanism. Submarine volcanic eruptions were known to produce tsunamis, but they were considered a secondary mechanism, and the warning systems were not optimized for them. This is a real gap, and it is one that the 2022 Hunga Tonga eruption made visible to the world in a way that earlier events had not. The Hunga Tonga tsunami arrived through multiple mechanisms simultaneously: water displacement from the eruption, atmospheric pressure waves coupling into the ocean surface, and collapse processes within the volcanic edifice. The standard tsunami warning system, which had been designed for an earthquake-driven mechanism, did not catch the volcanic mechanism in time at many locations. Pacific Basin warning protocols have been substantially updated since then, with new sensors and new detection algorithms specifically designed to catch the kind of multi-mechanism tsunamis that submarine volcanoes can produce. Those updates apply to Titan Ridge. The warning systems that would respond to a hypothetical collapsed tsunami from Titan Ridge are better now than they would have been before 2022. The institutional knowledge of how to interpret a submarine volcanic event for tsunami potential is more mature. The data products that the Pacific Tsunami Warning Center and other authorities use to characterize volcanic events have been expanded. The system is more capable of warning the relevant populations than it would have been a few years ago. That is real progress. The Ritter Island comparison is the right comparison to make because it is local, it is documented, and it demonstrates the actual mechanism by which a submarine volcanic structure in this arc has produced a deadly tsunami in the past. It is not the right comparison to make if you take it as a forecast for what Titan Ridge is about to do. Titan Ridge is currently a moderate submarine eruption at uncertain depth in a tectonically active region. Ritter Island in 1888 was a subaerial volcanic island whose flank had reached a critical state. The two systems are not at the same point in their respective trajectories. What they share is the broader arc, the broader geology, and the demonstrated capability of submarine volcanic structures in this region to produce tsunami-generating collapses under the right conditions. And what we do not know about Titan Ridge is whether the right conditions are developing, because we do not have the data to know. The depth that would tell us whether cone construction is progressing is not measured. The structural geometry that would tell us whether the flank is stable is not mapped. The internal state of the magma system that would tell us whether the eruption is escalating or settling is not characterized. We are watching the volcano through indirect signals, and the signals are telling us the eruption is active and changing, but they are not telling us whether the system is on a trajectory towards something more dangerous. So we watch, and we watch in the context of an arc that has produced flank collapses before, and we watch with the knowledge that the depth question, the one we keep coming back to, is exactly the question that determines whether the flank collapse pathway is something to be concerned about in the immediate term or something to file under remote possibility. But there is one more historical comparison that we need to make, and it is the one that has shaped how the world now thinks about submarine volcanic hazards. The lessons of Hunga Tonga are why Titan Ridge is being taken seriously, even though it is currently nothing like Hunga Tonga. We need to talk about that. Part 12. Why the Tonga comparison is earned. I want to be careful about how I set up this comparison, because it is the kind of comparison that can easily slip into hyperbole. Titan Ridge is not Hunga Tonga. The eruption at Titan Ridge has not produced anything close to a Hunga Tonga scale event. The current activity is 2 orders of magnitude smaller in plume height than the Hunga Tonga column. The thermal output is meaningfully less. There has been no detected atmospheric pressure wave at Titan Ridge. There has been no comparable tsunami generation. The events are not at the same scale, and saying they are would be wrong, but the comparison is still earned. The comparison is earned for a different reason than scale. It is earned because Titan Ridge belongs to the same broad category of volcanic system as Hunga Tonga, a submarine volcano in a tectonically active part of the Pacific, whose most important physical processes happen below the waterline, where direct observation is impossible. The category is the relevant thing. Within that category, Hunga Tonga is the event that demonstrated what the upper ceiling capabilities of these systems can look like. Titan Ridge sits somewhere in that category at a much lower scale, but the same category nonetheless. Let me walk through what Hunga Tonga did in January 2022, because the events are worth keeping in mind as a reference point. The Hunga Tonga Hunga Ha'apai volcano had been growing in the South Pacific for years before the climactic eruption. It had built a subaerial caldera structure that connected what had been separate small islands into a single connected feature. The volcano had been intermittently active. It was on the watch list of the Tonga Geological Services, and then, on January 15, 2022, it produced an eruption that registered globally on essentially every monitoring system humanity has. The eruption column reached approximately 55 to 58 kilometers above sea level. That is into the mesosphere. The eruption injected approximately 150 megatons of water vapor into the stratosphere, an amount large enough to measurably affect global atmospheric chemistry for months. The atmospheric pressure wave generated by the eruption propagated around the planet multiple times and was detected at every barograph station in the world. The tsunami generated by the eruption reached coasts across the Pacific Basin and affected locations as far away as Peru and Chile. The volcanic explosivity index for the event was approximately 5.8. It was the most powerful volcanic eruption since Mount Pinatubo in 1991, and arguably more globally consequential than Pinatubo because of its location and the specific atmospheric pathway it took. What made Hunga Tonga particularly important for understanding submarine volcanic hazards was not just the scale, it was the multi-mechanism nature of the tsunami it generated. The Hunga Tonga tsunami was not a single classical wave. It was a combination of several different physical mechanisms operating simultaneously. The eruption itself displaced water, as the underwater portion of the system delivered material into the water column. The atmospheric pressure wave coupled into the ocean surface and produced its own gravity wave, the so-called Lam wave, which propagated ahead of the conventional tsunami at the speed of sound in the atmosphere rather than the slower speed of a normal tsunami. The volcanic edifice itself underwent partial collapse processes that displaced additional water. All three of these mechanisms contributed to the observed tsunami signature at different locations and arrival times. The standard Pacific tsunami warning infrastructure, which had been designed primarily for earthquake-generated tsunamis, did not catch all of these mechanisms in time at every location. Some communities received warnings that turned out to be inadequate. Some communities received warnings that came late. The mechanism that produced the early waves at distant locations, the atmospheric Lam wave coupling, was not part of the standard tsunami warning algorithm, and at some Pacific coasts the first wave to arrive was not the one the warning systems had been designed to predict. The institutional response to Hunga Tonga has been substantial. Pacific Basin tsunami warning protocols have been updated to incorporate multi-mechanism tsunami generation. New sensors have been deployed. New detection algorithms have been developed. The institutional knowledge of how to interpret submarine volcanic events for tsunami potential is now meaningfully better than it was in early 2022. This is one of the few cases in modern hazard management where a major event led directly to substantial improvements in the warning system. Those improvements apply to Titan Ridge. If the volcano were to produce a hypothetical tsunami-generating event, through cone collapse, through phreatomagmatic explosion, through some other mechanism, the warning systems that would detect and respond to that event are better now than they would have been before Hunga Tonga. The relevant authorities are more prepared. The relevant data products are more developed. The relevant institutional pathways are more practiced. This is real, and it matters. But the deeper lesson of Hunga Tonga is the one that bears on Titan Ridge most directly. The lesson is that submarine volcanic systems can produce hazards through mechanisms that are not the ones warning systems were originally designed for. The danger is not in the part of the eruption that is most visible. The danger is in the part of the eruption that is least visible. The above-water expression of a submarine volcano, the plume, the discoloured water, the surface thermal anomaly, is downstream of what is actually happening at the vent. The dangerous physics happens at the vent itself, in a part of the system that we cannot directly observe. Hunga Tonga had been producing modest surface signs of activity for some time before the January 15th climactic eruption. The system had been watched. The volcanic warning level had been adjusted at various points. But the specific transition from a moderately active submarine system to an event that registered globally was not predicted in advance, and arguably could not have been predicted given the data and understanding available at the time. The system did something that the surface signals did not telegraph clearly enough to forecast. Titan Ridge is at much lower scale. It is not on a trajectory that would lead to a Hunga Tonga class event by any reasonable extrapolation of the current data, but the category of system, a submarine volcano at unknown depth in a tectonically active region, with limited direct observation capability and a complex internal plumbing, is the same category. The same physics applies. The same uncertainties about what the surface signals can and cannot tell us apply. And the Hunga Tonga lesson, which is that this category of system can do unexpected things, applies to Titan Ridge as it applies to every submarine volcano on Earth. The honest framing is that Titan Ridge is being watched the way it is being watched because the category of system it belongs to has demonstrated the capability to produce serious hazards. The watching is appropriate. The framing of "this is the kind of system we need to take seriously" is appropriate. The framing of "this specific system is about to produce a catastrophic event" is not what the data supports. The middle position, that the system is in active eruption, that the trajectory is uncertain, that the depth is unknown, and that the appropriate posture is sustained monitoring rather than either dismissal or panic, is the honest position. And that is the position the relevant institutions are taking. The Rabaul Volcano Observatory is watching. The Smithsonian Global Volcanism Program is cataloguing. The Darwin VAAC is issuing aviation advisories. NASA Earth Observatory is publishing analyses. The Pacific Tsunami warning systems are monitoring for any sudden change. The maritime authorities are advising vessels. The institutional response is proportionate. The watching is happening. What is missing is the data that would let us answer the depth question, and the data that would let us answer the depth question is missing because of the logistics of submarine volcanology in remote ocean locations, not because of any failure of will or interest. So we sit with the situation as it is. A volcano is erupting in the Bismarck Sea. The eruption is in its second pulse after appearing to quiet. The plume is reaching 5 kilometers above sea level. The Pumice is reaching the shores of the Admiralty Islands. The fishermen are dealing with floating volcanic rock. The thermal output is in the high classification. The vent depth is unknown. The flank stability is unverifiable. The category of system has produced serious events before, locally at Ritter Island in 1888, and globally at Hunga Tonga in 2022. The institutions are watching, the data is being collected, the answers we want are not all available. That is the situation. And it leads us finally to the deeper question that has been sitting underneath this entire video, the question that makes Titan Ridge less of a unique story and more of a window into something larger about the planet we live on. Part 13. What the ocean is hiding. The depth at the vent of Titan Ridge is unknown. The flank stability of any cone being constructed by the eruption is unverifiable. The structural geometry of the active vent system is uncharacterized. The internal state of the magma supply is uncertain. The future trajectory of the eruption is unforecastable beyond the next few weeks of probable continued activity. The volcano is being watched through every instrument that can be brought to bear on it from a distance. Satellites, hydroacoustic networks, aviation advisory data, maritime observations, ground-based seismic stations. And the picture that all of those instruments together produce is still missing the most important physical parameter that would let us interpret the system in detail. This is not unique to Titan Ridge. This is the standard situation for almost every submarine volcano on Earth. The total magmatic flux from submarine volcanism worldwide is larger than the total magmatic flux from land volcanism. Most of the magma that erupts on this planet erupts into the ocean. The mid-ocean ridges alone produce something on the order of 20 cubic kilometers of magma per year, distributed across the thousands of kilometers of ridge segments that crisscross the deep ocean basins. The submarine portions of subduction zone arc systems like the Bismarck arc produce additional volume. The seamount chains scattered across the ocean basins, formed by hotspots beneath the moving tectonic plates, produce more. Add all of it together, and you get a picture of a planet whose volcanic activity is overwhelmingly an underwater phenomenon, with the land volcanoes that we tend to focus on representing a relatively small fraction of the total. We see almost none of it. The mid-ocean ridge eruptions are kilometers below the surface, at depths where the surface signals are completely suppressed. They happen continuously, somewhere on the planet, on timescales of weeks to months between individual eruption events. We sometimes detect them through the hydroacoustic networks, but the detection is sporadic and the identification of specific source volcanoes is rare. The seamount eruptions are similarly invisible at depth. The subduction zone submarine eruptions like Titan Ridge are the ones we are most likely to see, because they often happen at shallower depths where the surface signals can break through. But even within this category, the eruptions we catalogue are likely a minority of the eruptions that actually occur. The Smithsonian Global Volcanism Program Catalogue, which is the most comprehensive list of volcanic systems we have, contains a few thousand volcanoes. Estimates of the actual number of volcanoes on Earth, including all the submarine systems that have erupted within geologically recent times but have never been catalogued because nobody has ever observed them erupting, run from tens of thousands up into the hundreds of thousands. The catalogue is the tip of an iceberg. Most of the iceberg is underwater, in the dark, in the cold, at pressures and depths where the standard tools of volcanology cannot reach in real time. Titan Ridge broke the surface. That is the only reason we know it exists. If the eruption had been 100 meters deeper, if the gas content of the magma had been a few percent lower, if the eruption rate had been 20% less, the surface signals might never have crossed the threshold of detectability. The volcano would have erupted for weeks, would have produced its pumice and its thermal anomaly, and its hydroacoustic signature, would have run its course at depth, and the only record of it would have been a few unattributed signals in the hydroacoustic catalogue from a region of the Bismarck Sea where the analysts could not identify a source volcano. We would never have known. The eruption would have happened, and we would not have known. This is the situation we are in for most of the submarine volcanism on this planet. Right now, as you are listening to this, somewhere in the deep ocean, a volcano is probably erupting. Maybe several. We are not seeing them. We will not see most of them. The ones we do see, like Titan Ridge, are the ones that happen to be vigorous enough and shallow enough to break through the ocean's filtering, and that happen to do it in a part of the ocean we monitor closely enough to catch the surface signals. The information gained from Titan Ridge is not really about Titan Ridge. It is about the category of activity that Titan Ridge represents. Each submarine eruption we catch teaches us something about the systems we cannot catch. The hydroacoustic signature of Titan Ridge becomes a reference for analysing the signatures of uncatalogued events. The thermal pulse pattern becomes part of the library of patterns that Mirova uses to characterise submarine eruption regimes. The vent reorganization that Titan Ridge underwent on June 1st becomes part of the documented behaviour of multi-vent submarine systems, useful when we try to interpret partial signals from systems we know less about. The eruption is an experiment that the planet is running, in a part of its surface we mostly cannot observe, and we're doing our best to read the experiment from the sparse data that reaches us. The depth question, the one that has run through this entire video, is the question that frames how much we can read. If we knew the depth, we could place Titan Ridge precisely within the existing understanding of submarine eruption regimes. We could estimate its energy budget. We could project its likely evolution. We could assess its hazards with more confidence. We do not know the depth, and so we cannot do any of those things precisely. We can only do them in ranges, with caveats, with honest uncertainty about which side of the depth boundaries the system actually sits on. The danger of the depth being unknown is not the danger of any specific outcome. The danger is the danger of operating with reduced information. Every uncertainty in the input compounds into uncertainty in the assessment. The assessment of whether the eruption will continue, whether it will escalate, whether the cone will become unstable, whether a tsunami pathway is plausible. All of these assessments are degraded by not knowing the depth. We can still make them. We can still arrive at reasonable best estimates. But the confidence intervals around those estimates are wider than they would otherwise be, and the wider intervals mean that more outcomes are inside the range of plausibility. The Pacific tsunami warning systems are watching for any sudden change at Titan Ridge. The maritime authorities are advising vessels. The aviation authorities are issuing ash advisories. The volcanological community is publishing analyses as the eruption evolves. The people on the Admiralty Islands are dealing with pumice on their shores. All of this is happening. The volcano is being watched, taken seriously, and integrated into the institutional response to a real ongoing eruption. What you should take away from this video is not a forecast. It is not a prediction that Titan Ridge will or will not do something specific. It is a clearer understanding of what we know, what we do not know, and why what we do not know matters. The eruption is active. It is in its second pulse. The plume is reaching 5 kilometers above sea level. The pumice is reaching the shores of inhabited islands. The thermal output is in the high classification. The depth that controls the hazard profile is unconfirmed. The category of system has produced serious events before. The institutional response is appropriate. The watching continues. And underneath all of it, there is a deeper recognition. The Pacific is not transparent at Titan Ridge. The Pacific is not transparent almost anywhere. The volcanism on this planet is overwhelmingly an underwater phenomenon. The eruptions we see are a small fraction of the eruptions that occur. Titan Ridge is showing us, in real time, how much of the planet's geological activity is happening just below the threshold of our ability to observe it. The volcano is signaling to us through every channel it can: hydroacoustic pulses, drifting pumice, satellite thermal anomalies, an ash plume that breaks through the water column to reach the sky. Each of these signals tells us something. None of them tells us the depth, and the depth is the question that controls how much the rest of the signals are worth. Less than 1% of the people on this planet understand how dangerous this particular Pacific volcano is getting. The number is not the most important part of the sentence. The most important part is the word getting. The eruption is not static. It is in motion. It has reorganized once. It is pulsing now. It might continue. It might escalate. It might collapse the cone it is probably building. It might quiet down for years and then start again. We do not know which. We are watching. The ocean is hiding the main event from us, and the ocean has been hiding the main event from us for as long as humans have looked at the ocean. The only thing that has changed is that we are now better at reading the surface clues. Titan Ridge is what those clues look like in real time, for one specific volcano in one specific corner of the Pacific. The lesson is not just about this volcano. The lesson is about how much of the planet is doing things we're only beginning to learn how to read. And tonight, somewhere underneath the central Bismarck Sea, the volcano is still pulsing. The plume is still rising. The pumice is still drifting toward the shores of the Admiralty Islands. The hydroacoustic networks are still listening. The satellites are still passing overhead. The depth is still unknown, and the ocean is still hiding what we most want to see. There is a way of thinking about this that I want to leave you with. For most of human history, the things on the planet that could harm us were the things we could see. We learned the shapes of the dangerous animals. We learned the look of the dangerous weather. We learned the smell of fire and the sound of falling stone. The dangers we have not learned to read, even now, are the ones whose signatures arrive in forms we have only recently built instruments to detect. The plume of a volcanic eruption is something humans have known about for as long as we have existed. The hydroacoustic pulse of a magma fragmentation event at 600 meters depth in the central Bismarck Sea is something we have known how to read for about 70 years. The thermal signature of an active vent measured through hundreds of meters of seawater by a satellite in polar orbit is something we have been able to do for about 20 years. The ability to detect submarine volcanoes from space is so new in the context of human history that the entire discipline of submarine volcanology has barely had time to develop the standard libraries of patterns that would let us know what we are looking at. Titan Ridge is teaching us how to look. The instruments are recording. The patterns are being added to the library. The next submarine eruption that produces a signature like Titan Ridge's will be slightly easier to interpret because we will have Titan Ridge to compare it to. The one after that will be easier still. We are, slowly, building the ability to read a part of the planet that has been mostly opaque to us for our entire species' history. Each eruption that we catch in the act, like this one, adds another data point to the project. That project is going to keep going. There are submarine volcanoes erupting right now, somewhere on this planet, that we are not seeing. There will be more next week. There will be more next month. There will be more next year. Most of them will pass through their entire eruption cycles without ever being catalogued. The Pacific will keep doing what it does, moving its plates, building its ridges, opening its vents, releasing its energy into the ocean and into the atmosphere, and the human ability to track it will keep slowly improving, and the gap between what is happening and what we can see will keep slowly narrowing. Titan Ridge is one moment in that long process. The volcano is signaling. We are listening. The signal is incomplete. The listening is incomplete. And the process continues. That is the situation. That is what we know. That is what we do not know. And that is why this volcano, more than almost any other story we have covered, deserves to be watched not just for what it is doing now, but for what it teaches us about every other volcano on this planet that is doing the same thing just out of our sight.